All right, so last time we got to see a little bit about convex geometry. We started out talking about simplices, then we moved on to the concept of barycentric coordinates and orientation. Then we got to see what half spaces are. We learned about convex polytopes and two basic ways that you can represent them, either as convex combinations of vertices or as intersections of half spaces. And we introduced the problem of converting from a vertex representation to a half space representation. And today we are going to talk about that problem, which is commonly called the convex hull problem, in the context of 2D convex polytopes, or polygons, right? So a polytope in 2D is called a polygon for reasons of convention. So we're going to see a couple of different algorithms for doing this. And if you recall, last time we saw how you could solve the problem of computing a convex hull using Fourier-Motzkin elimination, which ends up being, hilariously inefficient. And we'll see a couple of other alternative approaches for 2D that use the specific geometric and topological properties of the plane and allow us to achieve much, much faster algorithms. Yeah?
So we went over the Fourier, I forget the other guy's name, we went over that algorithm for solving a system of inequalities.
Linear inequalities is the key point. They have to be linear inequalities. Yep. So what it does is it doesn't solve the system of linear inequalities, but allows you to eliminate a variable. And the way that it works, right, is that you can imagine that what Fourier-Motzkin elimination does is it takes an H polytope representation of a convex polytope and projects it to a lower dimensional H polytope representation. And what this allows us to do is that if you think about what a V polytope is, you can imagine that it's either a convex combination of vertices, or if you think of it in the sort of higher dimensional space where the weights just become additional parameters, then it can actually be thought of as an H polytope, sitting in some D plus n dimensional space, right? Then all that you have to do in order to convert that higher dimensional H polytope into a D-dimensional H polytope is project out the last n variables. So just kill them off. And Fourier-Motzkin elimination is just a technique for killing off one variable. And you just iterate that n times, and then at the end of the day, you're left with an H polytope in D dimensions. So that's the basic process for doing that. And it's very general, works in any setting, any dimension that you'd like. But we don't care about general for today. We're only going to focus on 2D. And the 2D algorithms will turn out to be a lot more efficient. So if you recall, the complexity of using Fourier-Motzkin elimination to compute a convex hull was something like n to the 2 to the n, right? Something like that. It was pretty bad. Yeah. So today we're going to see some better algorithms for doing this. But to do this, we have to first say a couple of things about how we're going to do computations, right? Or how we're going to write algorithms. So, usually if you start out in early algorithms course, many of these issues are just kind of brushed aside or swept under the rug. But models of computation, in the sense of what sorts of operations you're allowed or how you're going to think about the actual model of the machine that you write programs in, become very important, especially as you try to get more precise or higher performance algorithms. So things like the structure of memory within your system, or the types of numbers that you're allowed to encode within it. And so in this course, we will usually write algorithms in terms of a model called the real RAM model, or sometimes the Blum-Shub-Smale model. And it's a very sort of simple model of a computer, right? It's also fictional. They don't exist in reality, but it's a useful theoretical construction for writing algorithms in computational geometry. So in the real RAM model, we're allowed, the state of a real RAM computer has basically four components, right? So we have 4 parts. We have basically our instructions, which is our program. We have a program counter. we have a finite set of registers, and then we have memory. Right? And so this is, pretty standard, just like a word RAM model. The key difference is that these registers in memory, right, can be real numbers. So they're just arbitrary, values in R, right? And the basic sorts of instructions that we have sit into one of three different categories, right? So three types of operations. Will allow for load store. So basically just like, read and write a register to RAM, pull stuff in, write it out. Branch instructions, so you can have jumps and subroutines and so on. And arithmetic. And each arithmetic instruction just calculates some rational function of the input. So this basically computes something of the form like p x1, x2 to xn divided by q x1, x2, where these are both polynomials with real coefficients. So that's the basic operation, right? And this turns out to be a pretty powerful model of computing. It's not a very realistic model, but it's convenient for writing out geometric algorithms, and it's the one that we're going to work with today. We'll start to revisit some of these assumptions in a later lecture when we come to the issue of numerical robustness and how you actually go about implementing geometric algorithms. But for now, this is a working system, and we won't have to worry too much about the details of how this would actually be implemented practically. So a couple of quick notes. Many of your favorite lower bounds from regular algorithms hold in the real RAM model. It's actually like a stronger model of computation. So if you can prove something here, you can often prove it in some other model. But sorting an array is still order n log n, right? Or omega n log n, if you want to do it properly. So there's like no way to sort an array of n items faster than order n log n. And if you recall, we saw that we could reduce the problem of computing planar convex hulls to sorting, right? So there was planar convex hull. I didn't say this very carefully last time, but I'll do it again right now. So the trick is we have this lifting map, right? So we have a technique called a parabolic lifting, right? Which basically takes a point. I'll say it in a sort of special case, but we'll come back to it later, which maps real numbers to real numbers in the plane according to the rule x maps to the pair x squared. So if we draw a picture where we have, like, say, a bunch of different points here on a line, right? So we'll say, let me draw this lower. So suppose we have a bunch of points x0, x1, x2. Right? These are all living on the line R. Then when we apply this sort of lifting map, they all get projected onto the surface of some parabola out here. The parabola like y equals x squared, something like that. So this guy ends up mapping to this point x0, x0 squared, x1, x1 squared, and so on for each of these points in our set. So the interesting thing is that if we choose to represent the convex hull of all of the supporting hyperplanes in the convex hull as pairs of vertices. So we're going to use the sort of primal representation for each of these things. Then constructing this convex hull will give you these pairs of points, drawing these supporting lines like this. We'll think of this as basically the line x0, x1, x1, x2, etc. So given these pairs of lines, you can very easily reconstruct a sorted order of the original sequence, even if they were given to you in some arbitrary order, by basically lifting them up to this parabola and then computing a planar convex hull, right? And then just walking these little pointers that you get here in order to build a sorted list. So this basically implies that planar convex hull of n points takes at least n log n time in real RAM. So that's kind of the little bottom line from that result. Okay? So this is sort of our starting point. So we know that the lower bound here is n log n, and then we have a terrible upper bound, which is super exponential. But we can, do better than that. So one simple algorithm, which beats the super exponential bound, or a simple polynomial time algorithm for computing the convex hull of a set of points in a plane, is to just brute force scan through every possible line between every pair of points, and then just test if it's a supporting plane. All right, so the first algorithm that we're going to talk about today for doing convex hulls is brute force search. So here's, so let me just, for the sake of reference, we'll state the problem here precisely, right? So this is the problem, planar convex hull. Right, our input is going to be n points. Right, it is basically P1 contained in R2. We'll just write it like that for now. So we'll work in sort of an affine system for the moment. And our output is going to be H half spaces generated by pairs of points, Pi, Pj, right? We'll call this thing H sub k, right? Such that the convex hull of P equals the intersection of all I. H, Hi, right? And then this, these should be minimal, right? So we'll require that these half spaces are basically right. So that's kind of the problem that we want to solve, right? So we want to find the smallest set of half spaces which will generate this set by intersecting them. And of course, we have a picture here. So these points would be P, and then these planes here would be H, right? So this would be like H0, H1, H2, H3, H4, etc., right? And then they're sort of oriented so that their intersection contains the complete set. All right. So that's the problem. So here's our trivial algorithm. Test all pairs of points. How does this work? Well, okay, anyone want to take a guess at this? Right, so we'll start out by saying, well, okay.
The brute force one?
Yeah, this brute force algorithm, right? I kind of sketched it out very quickly, but we'll just kind of say how this works really fast. So we'll say for pair of points pi, pj. Actually, we'll make it an ordered pair. So for every ordered pair of points, we'll say for every p sub k in P, say if the orientation of pi, pj, pk is greater than or equal to 0, right? Do I want to use greater than or equal to 0 or whatever, right? Well, it's not going to be too important. We'll just say continue outer loop, right? We'll put a label here. So basically just say discard this point. Otherwise, we'll create a hull up here. Otherwise, hull basically gets hull plus the list containing pi. All right, and then when we're all done, we'll just return the hull. So this is the simple approach. And so what would be the time complexity of this loop as a function of n? So keeping the dimension fixed, right? How many iterations do we have to, or how many operations, if we think of this comparison as our operation, would this loop require? Right?
Thank you.
Exactly. Right. So the time complexity is order of n cubed. And the real problem with this algorithm, right, is that we're basically like repeating a bunch of work over and over again. We're kind of like every time, we test like another like edge, we have to insert it into this set and then, re-verify it. So a slightly smarter approach to this would be to imagine that instead of just iterating over these points in some completely chaotic or arbitrary order and continually retesting things, we'll keep the current hull as it exists and then insert the points into it one at a time. So we'll imagine doing a kind of incremental insertion. All right, and the key to this is to basically realize a few things about 2D convex hulls, which is that in a 2D polygon, right, the boundary of the polygon is going to be topologically a circle, right? So that means that we can actually encode each of these half spaces as an ordered list of points, rather than as some ad hoc collection of half spaces, right? So we'll say this a little bit more precisely.
Until the video lectures are up and clear, could you actually just erase the first half of your writings and then leave the second half up, in case like if you have a graphic or something we want to like write it out? Does that make sense? Or?
Yeah. Well, I think that this is going to be fine. I want to leave this section here for now, right? Because I'll reference these parameters n and h as I go through the algorithms. All right. So, okay. So here's sort of the observation. This is a topological fact. I won't prove it because it actually turns out to be a slightly involved process, which we won't get into. But it's intuitively obvious that the boundary of a V polytope in 2D is a circle. Right? The conclusion is that we can encode the facets as an ordered list of vertices. So for example, going to this picture here, let me get like a marker. So suppose we call this point here P0, P1, P2, P3, P4. So these are our boundary points. Then we could store a list here, P0, P1, P2, P3, P4. All right, so this would basically be, our vertex representation, or the vertices on the convex hull stored in this list. And then the actual hull would just be the set of pairs of these vertices. So we can imagine that we'll have, P1, P2, etc. And then when we get to the end, we have to loop around. So it'll go from P4 back to P0. So we have this ordered list of pairs. Right? In 2D, this is sufficient. This does not work in higher dimensions. It's sort of an artifact of 2D geometry. Right? But we can use it to simplify calculating a convex hull in 2D substantially. So here is the basis for the next convex hull algorithm that we're going to use, is that we will basically maintain just this list, and then every time we see a new vertex, by walking through this set of points in arbitrary order, we can just scan through this list and figure out where we would like to insert it, or just do some update to this list in place. So how would we do that? Well, okay. Imagine I have a set of points here. All right. Forming some convex polygon. And I have a new vertex here. Call it x. All right. Then if I look through this list of points, I have a pair of these lines which are tangent to this polygon. And all of these edges within these pair of tangent lines just need to be deleted and then replaced with this edge and this edge. So we can make this a little more precise by saying that an edge, pi, pj, is visible from x if orient pi, pj, x is less than 0, which I think is consistent with our stuff. So let's suppose that we're going this way when we orient the edge. So imagine we go from pi, pj to x. I believe the convention we used was right-hand rule, so we should actually make this greater than 0 in order to be correct. Actually, it should be greater than or equal to 0. Right. So remember the orientation test from the last lecture where we basically calculate this using just a determinant, basically, of the points. Right? Another way to think about it in 2D is that the orientation test determines whether or not a point is to the left or to the right of a line. And so if this point x here is to the left of this line, then this line here is visible from x. And so our incremental algorithm for constructing the convex hull is to maintain this list of vertices, and then every time we get a new vertex, we scan through that list and then remove all of the edges which are visible from X and replace them with a new set of edges that just connect to X, right? So we'll basically replace these two edges in this vertex with a pointer to X and a pointer down there. All right? So how does this look in detail? How am I doing for time? All right, good. So, yeah?
So what, where does the observation of the boundary of the view polytope in 2D is a circle?
I did not prove this.
But what is it?
It just means that if you have a ball in 2D, right, or what's called like a contractible space, then the boundary of this ball, right, which are the set of all of the points that are, you know, on the surface. I mean, I'm saying this in a sort of circular way, right? Then it will look like a circle, right? In general, like a ball in d-dimensional space has a boundary which is a d-sphere, right? So in 2D, like the boundary of a disk is a circle. In 3D, the boundary of a ball is a sphere. In 4D, you get like a three-sphere, and it becomes like a little bit weirder, but that's kind of the pattern as these things progress. We'll revisit some of these things later on, right? For now, we're just going to take it as a given that you can actually encode the boundary of a 2D polygon as an ordered list of vertices, right? This is not true in higher dimensions, though. Like, there's no analogous encoding. It's just that in 2D, basically two manifolds, right, like little blobs, will just look like different potatoes, and their boundaries are just going to be loops, right? So the boundary of any two manifold will just look like a system of loops, which are all nested together in some way, right? So you can store, polygons as like lists of vertices. This is a kind of special thing in 2D geometry, and one of the things that makes 2D convex hulls much simpler, right? In 3D, you have, maybe something that looks like, this. All right, so you can have like some weird structure. So imagine this is like a set of tubes that go off into space, and they can loop around and connect in different ways. And so it becomes more complicated. But we won't worry about that for now. We're in 2D, and we're working with convex hulls, which are convex sets, which are all balls. And so we can always store things as lists like this, right? So that's the advantage of 2D. All right, so yeah, now on to the next thing. So I wanted to finish up this incremental algorithm here. So we have this concept of a visible edge, right, which is basically done by just checking the orientation. We can store the vertices using a list. So all we're going to do is just go through and then clean up parts of this list, insert the point in there, and then update it. So let's do the, let me just quickly write out how this code works. All right. So here we go. We have an incremental convex hull. So again, we'll kind of keep our same inputs and notations, and this is a sort of pseudocode type algorithm. So the starting point is we're going to have this list, which we'll call CH for the convex hull, and we'll just initialize it with P1, P2, P3, assuming that n is at least 3, right? Because otherwise it becomes trivial to compute the convex hull. And we're going to require CH is initially counterclockwise. So just, if they're not counterclockwise, flip any two of the vertices and it'll be, correct, right? So you just have to enforce that invariant. Then we'll say, okay, so for I equal 4 to n. So we're going to loop over all of the remaining vertices. And then once we get a new vertex, we have to insert it into this list here. So what we'll say is for j equal 1 to the length of ch. Or let's use 0 index for this thing here. We'll read out a pair of points. So these will basically be the two successive points in the convex hull. So A is equal to ch at point j. Mod. And we'll say, OK. So basically, we'll imagine that we're going to loop over all of the faces, right? So AB becomes one of the faces in the convex hull. And PI is the point that we're going to insert. So we'll say if this edge is visible from this point. So we'll basically say if orient A, B, PI is greater than or equal to 0, and if the previous edge was not visible. So that will basically be if the orient of, I guess it should be ch j minus 1 plus 1 ch, whatever, just the previous one. Assume cyclic indexing onto ch, right, because it's basically going to be a circular array. Don't want to write it out, and also it's not even going to show up on the camera. A pi is greater than 0. Or no, less than 0. Then we'll basically, let's create a new array here. Right, we'll call this one NCH, because I'll need to kind of copy the whole array into it. So basically what we'll imagine that we're doing is instead of modifying it, we're just going to build a new array as we walk over the list. So we'll set the NCH here is going to be equal to NCH concatenated with A and PI. So we'll add PI into the list. Otherwise, we'll just add A onto the list. All right, and we just do this, looping over all of the vertices. And then when we're all done, at this point here, we'll just set CH equal to NCH. And when the array is finished, we'll just return CH. So that's the incremental algorithm for computing a convex hull. So we just scan over the array, build a new list by basically processing each of the vertices in order. And when we're all done, we'll just return the final convex hull. Right. So anyone want to take a guess about how long this algorithm would take as a function of n? Or in other words, how many times does orient get executed asymptotically given n input points? So ideas here?
Squared?
Yeah, exactly. Right. So it could take up to quadratic time. Right. So the time complexity order n squared, right? And again, the space complexity is trivial. It's linear, right? So we don't have to worry about space complexity with any of these things. But would it always take quadratic time? Well, in general, yeah. Worst case, it could, right? But we could imagine, right, if these points were arranged in such an order that we got very lucky and that all of the points on the hull were in the first list, right, then we would actually initialize this list to basically only have the hull initially, right? So, imagine that basically like all of the points which were finally going to be on the hull were just in the first set of points that we copied into it. Well, after that, every successive point that we test is only going to be tested against those points on the hull, and we'll basically find that it's contained inside the convex hull, and then we can throw it out. So instead of testing every point against every other possible point, we're only going to be testing every point against every point on the hull. Now, this is not guaranteed, right? Because this assumes a fanciful thing that we started out with the points arranged in such a fantastic order that the points were just on the hull. But I claim that if the algorithm was arranged in such an order, then the complexity would be order n times h, right? Where h is the number of half spaces on the hull. Now, why is that better? Well, in general, h could be a lot worse, right? Or it could be about the same size as n, but it's always going to be at least smaller. And in practice, right, if we imagine that we have points in a plane, it's a reasonable assumption to assume that h would be about square root of n, right? So, reasonably, h is in little o of n, typically for randomly distributed points, h is in order square root of n, right? So why would this be? Well, if you imagine that you have like just a set of points which are uniformly distributed in some ball, right, then h is going to be roughly proportional to the area of that ball, whereas n will be proportional to the volume of that ball. And the ratio of the area to the volume will basically give you this square root term right there. So if we were lucky, this algorithm could take order n times h, right? If we were lucky. All right, now that's of course too much to hope for. In practice, these points are going to be distributed in some other order, so you can't really assume that things are going to run that fast. But it does motivate us to try to find some algorithm which could maybe realize this order n times h runtime. And so instead of having to do a fully quadratic sweep through all of the points, we could do it in maybe order n times h by inserting the edges onto the boundary of the hull in the order in which they occur as boundary edges. Right? So that's the goal that we would like to realize. And it turns out it's actually not even hard to do that. Right? And so that's our next algorithm, which we are going to see. So, one simple improvement over incremental convex hull. Right? And this technique is called the Jarvis march, or sometimes gift wrapping in higher dimensions or other settings. Right? Let me see, where did I put the, is this thing still good? Right. Right. All right, Jarvis march. So here's the basic idea, is that we want to look for only the edges which happen to be on the hull. So we're only going to consider these pairs of vertices as we're building the incremental hull by building up the edges around the boundary. So that is that once we insert an edge into the hull, it better stay there, right? So how do you do this? Well, I'll draw a picture first to illustrate how this works, and then I'll write out the code. So imagine we have these points in the plane, all right? So start from, say, the leftmost point, all right? It just has to be any extreme point. It doesn't matter, all right? Now here's the trick. If we imagine that we were walking along the boundary, starting from this point, then we should only ever take a right turn, right? So if I basically sweep through every point, right? So I start out by drawing a line here, then this point here will only be on the boundary if there is no other point to the right of it. So if I take this point, I can start here, and then just walk through the rest of the point set. So maybe I get to this point here. Well, OK, this point would be to the right of this line. So if I take this next point, this line would now have this point here. So I can then imagine, well, OK, this point can't be the next point on the hull. So we'll just move to this next point here and say that that guy is the next point on the hull. So we'll just pick that line as our next line going along the hull, right? So we'll just keep walking through the points. And then eventually, maybe you try this point, but it's to the left of this line, so that's OK. Then you try maybe this point here, right? Well, it's to the right of the hull, so you take this line going through there. Then you go to this point here. Well, OK, maybe that's to the left. But then finally you get here, and now you're done. So you add this edge to the hull, right? Then you repeat. So you go from this point, and then you run the whole show all over again. So you basically walk through, so for this point, you say, all right, sweep out a line between this pair of points. Is it to the left or to the right? Keep walking until eventually you come to the next point on the hull. And then you repeat again and again. And then you're done. So the idea is that you will only take the rightmost point starting from whatever vertex you happen to pick initially, right? And the key criteria to make all this work is that you have to start, of course, from some vertex which is on the convex hull. But that's easy enough to do. Just pick any direction and then just find the point which is farthest along that particular direction, and you have your starting point. So in pseudocode, you can explain what's going on here. which may or may not be illuminating, but I'll write it out. So here's the basic idea. Again, we'll return a list called convex hull, right? And we'll start it out as empty initially. And we'll say, OK, let I be the index of leftmost point. Leftmost is, again, arbitrary. You could take any axis. It would still work. And then define this variable a and set it equal to I. All right. Then we'll create a do loop, right? So do set b equal to a plus 1 mod. And this doesn't even matter. It just has to be anything that's not equal to a, right? I mean, you could just pick whatever random vertex. So then we'll say, OK, so for j equals 0 to n minus 1, I suppose. If pj is to the right of the line AB, then we're going to make pj our new b, right? So we'll basically say if the line p sub a, p sub b, right, pj, so if it's to the right, that means that the orientation should be greater than 0. No, less than 0. Less than 0. Then we'll set b to be j. All right. So after we're all done, b is now the next rightmost point on this list. Our convex hull will basically just concatenate the convex hull with just the point b. And then we'll set a to b. And then just repeat, do this until we get back to where we started. So while a is not equal to I. And then when we're all done, return the convex hull. So that's it. That's the very simple Jarvis march. All right? So does anyone want to take a guess at the complexity of this algorithm? I've already kind of told you what it was earlier, right? Time complexity. So it's a little harder to measure it because we have a while loop here. It's not like a simple for loop. But the thing to realize, right, is that the real question is how many times this outer while loop will get executed, right? And one way to observe this, right, is that every time we run this thing, we're going to append one vertex onto the convex hull. And by that sort of hand-wavy picture argument, we know that it will eventually terminate. And when it does, this convex hull has been filled up with all h of our vertices that are on the convex hull. So this outer loop executes h times, right? The inner loop, well, it's just a naive for loop over like all of the vertices, so that's going to execute n times. So the time complexity of this algorithm is order n times h. And this is an interesting feature of the Jarvis march and many geometric algorithms in general. So in a lot of standard classical algorithms and data structures, usually you have algorithms which just perform in, say, like always n log n time, regardless of their input distribution or whatever the output looks like. But in many cases, the size of the structures which you might construct in geometric algorithms could be very large or it could be very small. And so it makes sense to leave the output itself as a parameter that can vary as a function of your input. So in this case, because h has like an enormous amount of variability, it could be like way, way, way smaller than n, right? We would like to leave it as a parameter in our analysis of the algorithm. So the time complexity here is now actually better than n squared because h in general is going to be much smaller than n. And so this represents an improvement over the naive kind of linear search for constructing a convex hull. All right? So that's all well and good. We now have an algorithm. And actually, if it turns out that h was like way smaller than log n, then this would actually be better than the n log n lower bound. So from this analysis, this actually suggests that really, if we want to get the lower bound for convex hull correct, we should actually only consider the vertices which are on the hull itself to be part of the analysis. So the sort of simple update, taking into account this parameter h, is that the convex hull lower bound should really be n log h. So we'll basically point out that it can be omega n. And if we consider that maybe we did this, we could actually write it as basically order h log h, though it turns out you can come up with slightly tighter lower bounds, right? So we could just imagine that we would basically restrict ourselves to only calculating on the elements h and then leave the rest there. We won't get to such an ambitious lower bound in this class, but we'll come pretty damn close. And it actually turns out that you can make this a little tighter, with some more detailed analysis, and you get n log h as a lower bound. But we won't prove that today, or probably in this class. So, OK. So that's sort of like an h-sensitive lower bound, or it's what's called output sensitive. So parameters that depend on the size of the output are output sensitive parameters. And many times in geometry, we'll have more than one variable when we're computing time complexity. So there would usually be like n, dimension, number of points, some output parameters, and other variables will kind of show up. So we end up with much more detailed types of proofs. All right? So that's all well and good. OK. So this algorithm would actually be fantastic if h was smaller than log n, but usually that's not the case, right? So can we get to the n log n lower bound as we initially started out trying to achieve? Right, and the answer is yes. It turns out that it's actually relatively easy to get to n log n in 2D. Right? And most of these 2D algorithms which reach the n log n lower bound use a technique called sweeping. So the idea in sweeping is that you pick some parameter or some axis that you would like to treat as sort of a 1D problem, and then you can just sort all of the points along that axis and then process them sequentially using some trivial algorithm. So the first sweep algorithm that we're going to look at today is called Grams scan. And it's a simple modification of Jarvis March, right, which we just saw. Except instead of processing each vertex on the boundary of the hull, we will basically pick a particular vertex and then sort all of the vertices on the hull by their angle around that vertex. All right, so here's sort of the picture. Actually, I'll just erase this one. So here's the idea. You pick some starting vertex. Which has to be on the boundary of the hull. So basically, take any extreme vertex you'd like, say the leftmost vertex. Start from there. And then you sort each of the vertices in the hull by the angle that they form with this vertex. And this can be done, again, using a left-right test. So you basically can compare 2 points by checking whether they're left or right. So if you imagine if you look at the angle that this would form with, like, say, the vertical x-axis, right, then this point here forms some angle theta. Maybe this point here forms some angle alpha. So you can basically assign to each point some angle parameter and then sort these angles. In practice, this could be, again, implemented by just using an orientation test. Right? So given this order of points, we can assign them some numbering based on this angle that they form. So maybe this one is 0. This guy is 1, 2, 3, 4, 5, and 6. All right. So then when we want to build the convex hull for these points, we will do the same thing we did with insertion sort, or with the insertion convex hull algorithm. Except because they're being processed in sorted order, the insertion step becomes way easier. So here's the idea. If I start from this vertex, I can imagine that, well, OK, I start from 1. We'll call this guy, I don't know, say p negative 1, something like that. Connects to 0. Then we get to the next vertex 1 here. So we'll basically insert that into the hull. So now our hull looks like this. Then we get to 2. Well, for 2, we can basically start counting backwards from the top of the hull. So we see 1. Well, we can erase 1 from the hull, and we add this edge back in there. Now that vertex is done by just inserting it. Similarly, we get to 3, insert that. Then we get to 4. Well, the 4 covers 3, so we pop 3 off the hull. And now we're left with 4. Get to 5, repeat. And then eventually 6, and then we're done. So that's kind of the idea, is that as we insert them into the hull, we can basically pop backwards off the top of the hull as we're inserting them into it. Now, the interesting thing is that I claim inserting the vertices in this order, where we're always popping the elements off the back of the hull first, will allow us to construct this hull in linear time once they're sorted, right? And that ends up being way faster, right? And so the simple argument for why that is true is that every time a vertex gets inserted into a hull, it will only get removed exactly once. And then after it's removed, you don't ever have to look at it again. So in an amortization sense, we can basically pay a counter when we insert a vertex into the hull. And then whenever we delete it, we pop out that counter. And the total number of counters that we have to use is only going to be order n. So that's the simple algorithm. How am I doing for time here? All right, well, I'm a little bit low on time, so I'm not going to write out the code for it. But the idea is pretty straightforward here, and you can look this up in the book. I believe it's covered in like first or second chapter of the book. Now, there's a variation on this, too. This is not the only way to get to n log n. A better algorithm, so the complexity of gram scan, right, ends up basically being dominated by the complexity of doing that sort step in the first phase. Because once you've sorted them, inserting the vertices into the hull is a linear time operation. So the total time complexity of gram scan is n log n. But that initial step, where you have to sort all of the vertices, becomes rather expensive because you have to call orient a bunch of times. And so each time you call orient, you have to usually do some pretty nasty work that we'll come to probably when we get to talk about numerical issues. And it ends up being very expensive, right, doing those calls to orient over and over again. So it would be great if we had an algorithm which allowed us to save a few of those extra calls to orient, right? So we only had to maybe it takes still n log n work, but as long as the number of calls to orient is relatively small, then we would have some progress here. And so this is our second n log n algorithm, which is called the monotone chain method, right? So this is the monotone chain algorithm. And it is, again, a kind of sweep algorithm, except instead of sweeping by a polar angle, we're going to sweep along the x-axis, right? Or whatever. It doesn't matter if it was x. It can be any point that you want, right? So here's the idea. So here's the algorithm. So what we'll do is we'll take all of the vertices on our convex hull, or all of the vertices in our set, and we'll sort them by x. Right? So we have basically a set of events that are going to be processed along this axis. So, and instead of maintaining a single hull that we're going to insert them all into, we're going to maintain a pair of hulls. So we'll have one hull which is going to ride along the top of these vertices, and another hull which goes along the bottom. And we can use the same incremental insertion technique and the same argument to show that inserting each vertex into one of those hulls takes only linear time, amortized. So what we do is, as we're processing these vertices, we add this vertex here, add this one here, here, and here. And on the bottom, we build a second hull, again using the same incremental insertion technique here, right? And again, constructing either of these hulls takes linear time. But here's the key point. When we sort these guys, we only have to compare the x component of each vertex. And comparing the x component is way cheaper than comparing the angle that the two vertices will sweep out along the side. So this algorithm will take order n log n time, but the number of orient calls. Well, we only need to call orient whenever we're merging a vertex into one of these chains, and that becomes order n. So this is probably the go-to 2D convex hull algorithm if you're really looking to like just make something work right away. And in a more detailed type of analysis, you can also show that it has other nice properties like being cache efficient or cache oblivious, depending how you do that sorting step. And it's sort of like you're just simple catch-all, right? But it's not theoretically optimal because remember, the lower bound for the convex hull is n log h. It's not n log n. So with the remaining time, I am going to go through a very simple algorithm that will allow us to get to this n log h limit, right? And it basically is the culmination of all of the ideas which we've talked about so far for different techniques for getting convex hulls. Right. Now, in practice, there may still be reasons to prefer monotone chain, but this is a nice result, and we're going to go through it right now. So this technique is called Chan's algorithm. And the basic idea behind this technique is that if we suppose that we already knew h, right, then we could use the fact that we had some value of h that worked to generate an optimal decomposition of this problem so that we could solve the convex hull, right, problem for all of them. And the basic idea behind it, right, the reason that you can do this decomposition is that if you've already computed the convex hull for some set, then you can use that to speed up the Jarvis march, right? So imagine that we took our set of vertices, we cut it into tiny pieces, right? For each little piece, we'll compute a convex hull on each of those pieces. And then we can do Jarvis march over those pieces. But because each of those pieces is already a convex hull, we can use that to speed up the selection for the next vertex. So basically, the idea is that we're going to do Jarvis march, but we're going to do it faster, right? And the way that we'll get that speed up is by observing that for a convex polygon encoded as one of these lists of vertices, we can very quickly calculate tangents to that convex polygon for doing the insertion step. And this would also, by extension, give us a faster way to upgrade the insertion algorithm to make that run in n log n time too. So the basic idea, right? Well, there's a couple of ideas here, but the first is that if you have some set of points here, this is your convex polygon, and say I take another vertex out here, x, then you can compute these two tangent lines to x in log n time, right, or log h time. So suppose there's h vertices here, then you can find these two tangent vertices in order log h, right? So how do you do this? Well, the basic idea is binary search, right? So you have some list of vertices. We'll call it P0, P1, P2, P3, P4. And if it was a simple flat linear list, we could basically just use the fact that you have basically the constraint where x is either above or below this adjacent line segment, right? But because we're looking at a list of vertices, then it's a sort of circular list, and so we have to kind of break that symmetry in some way, right? But the predicate that we're basically searching on is if you take some p0, that we're going to require the next vertex after it is above the chain, and then the vertex before it is also above the chain, if we're trying to find the lower tangent line. So to find this tangent, we have to basically, we have a pair of predicates, right? One which is that this line here, right, is basically above that, and that x is to the right of this line. And then you have to basically scan through that. And I don't know if I'm going to have enough time to do this in detail. I think I'll probably make this one a homework exercise, because it's not a big deal to do it. So this will probably be part of your homework, is to calculate these two tangent lines. But suffice to say, this is not a difficult thing to do, right? So, OK. So now, how do we apply this idea to computing convex hulls or to doing Jarvis March? Well, suppose we have a bunch of different convex polygons, right? If I want to do, say, a Jarvis March starting from this vertex and find the next rightmost vertex, well, then I only need to look at the tangent lines for each of these little convex polygons which are left over. So what I can do is say start from this point x0, scan through, and then for each polygon, just check which tangent. So I have to only check this tangent, and this tangent. All right, so if I have, say, m total polygons, right, and each of them is of size h, then the complexity would be m log h for one Jarvis step. All right, so that's kind of the idea. So using that, we could basically say, well, OK, if the hull was of size h, right, then however many parts there were m, right? So, OK, we're going to suppose that we cut them into m pieces, right, into pieces that are all of size m. So then it would actually be n over m log n, right, something like that. All right, let me be more precise now. All right, I'm getting ahead of myself a bit.
Can't you just take the original thing and just keep on adding points in that way?
Yeah, that would give you a log n algorithm, but we want to get to n log h, right? So you could use this technique with the incremental algorithm to get an n log n algorithm.
Would it be n log h though? Because you have it's log h for the convex.
No, because each of them is still going to have to go through order n work, right? So that won't get you n log h, right? N log h is actually kind of tricky to get to, right? This algorithm is a somewhat subtle thing. So I need to just double check one thing and make sure I say this right. OK. So here's the starting point. All right. So OK, from this we can now say that, all right, we know how to calculate tangent lines efficiently in log number of vertices time. Or if you don't know how to do that, then that's a homework assignment. All right. Taking that as a building block, we'll start out with a very crazy assumption, which will turn out to be something that we can relax, right? But suppose that we knew the number of points on the hull beforehand. So we knew that it was h, all right? So we're going to create an algorithm where if we know the parameter h, then we're going to chop it up into blocks of size m and then use that data to basically like fuse the hull back together. So I want to make sure I get the algorithm correct here. So here's the idea. I'll just write out the code, but I want to kind of bring my laptop over here. So I have this here. So this is the basic idea. We're going to call it hull 2D. And we'll have our point set p as an input, m as a parameter, and then we have h, which is like the number of points on the hull. So the first step here is that we're going to split p into subsets of size n over m, or of size m. So we'll basically say, so first thing is we're going to basically split p into subsets of size m. And then these subsets will basically number them p1, capital P2, all the way up to p of n over m, right? All right, then for each pi, for each of these subsets, compute convex hull of pi using gram scan monotone chain, just any order n log n algorithm, right? It doesn't matter. As long as it's like n log n. Probably monotone chain would be what you'd want to use. Just dump it into some other smaller thing, right? OK. So now what we'll do is we're going to use each of these pieces, which we have now constructed convex hulls for, and we're going to run Jarvis March on the whole mess. So we'll say, OK, let's define a vertex P0, which is equal to rightmost point of P. And then for every point on the hull, so we'll basically say for k equals 1 to h, then for each piece, we'll just try testing that piece. So we'll basically say for I, for each pi, find tangent to, or I should actually say find rightmost tangent to P0. And this is basically done using that binary search method, which I kind of punted on a little bit due to time constraints. And basically set pk plus 1 to the tangent point which is farthest right. All right. And then we'll say, after all of this whole thing, we'll say if pk plus 1 equals p0, return. Otherwise, if this fails, then we'll say, you got h wrong. So we'll just say return fail. Right? So the algorithm will only work if we know h. Right? So basically, we're only going to do h iterations of this because we don't know how many times we're going to have to do this before we stop. But if we did happen to pick h that was at least as big as the number of points on the hull, then this will terminate. So what's the time complexity of this algorithm? It's a little bit tricky to see, right? So, so basically, we have this first step here where we have to split this thing into these subsets of size n over m and then construct the convex hull of each of them. So there are going to be n over m. So for this step here, the cost of this phase right. So there's basically n over m different convex hulls that we have to calculate. So we have n over m, but then times m log m, right? So there's basically the amount of work that we would have to do there. Or this ends up being just n log m. All right, so that phase. Then if we look at this, well, OK, we have to do h steps in the worst case, or else we're going to terminate, right? So how much does each of these h steps take? Well, this is going to take h times log of m, because each of these guys is at most like size m, right? So the complexity here is just h log m times the number of pieces, which is n over m, I believe. Is that correct? Did I do that right? No, so that should be h times, n over m times log of m. Yeah, that's right. OK? So that's our time complexity for this whole thing. So if we combine the two pieces, right, then the total time complexity of this algorithm is order of n times 1 plus h over m log m. So in an ideal world, right, if we wanted to try to optimize this thing, right, so suppose that h was like the number of points on the hull, then we could basically pick m equals h, and that actually would give us an n log h algorithm if we knew what m and h had to be a priori, right? So how do we get those parameters, right? This is the time complexity here. right? Well, the answer is we just run this thing in a loop, right? So we'll just do it a couple of times until we can actually get the correct parameter of m and h. So we'll basically start with maybe like an overly ambitious guess, say that there's maybe 1 point on the hull. And then if that doesn't work, well, it fails, and then we'll just try it again. And then every time we do this, we'll just keep increasing m until we get the right value of m, and then this all will cancel out, and life will be simple. So what strategy should we use for selecting m or running the search? Well, we don't want to do something too conservative, like step 1 point at a time, but we can't step too large or else we'd miss the whole thing. So the trick, right, and in the last 3 minutes, I'll basically write out how this works and probably erase this chunk here. So the trick is that we're basically going to run this thing. So we'll basically say, we'll call it Chan's hull algorithm, and we'll just give it the points p. And so what we'll do is we'll basically say for t equals 0 to n, right? We'll set m is equal to the min of 2 to the 2 to the t and n, the number of points on the hull. And then we'll say, we'll call ch, will just be hull 2d, run it with the point set p, m, and m. And we'll say if ch is not equal to fail, then return ch. We can actually just run this to infinity. I mean, it doesn't even matter, whatever. All right, so just keep stepping until you do it. So that's the simple algorithm for computing the convex hull points. Now, I claim that this algorithm will actually terminate in n log h. All right, and why is this? Well, we're basically going to just keep marching up m at increments of 2 to the 2 to the t. Right? So we're just going to be taking these really huge steps with t. Right? But eventually, we'll find an m that's sufficiently large that this gets done, right? And then we're finished. And so how much does this take if we pick m equals h? Well, the time complexity of this thing ends up being n log m, right? So
how does the n times 1 plus n over h?
Because I combine these two parts. I have this part here and this one. And I'm going to basically pick h equal m, right, when I'm plugging in the two parameters. Right, so I'm plugging in m, right?
I don't know. It looks like it would be...
h is a bound here, right? So I know it's going to terminate in at most h iterations, right? It's not being used for anything. So this capital H here is actually not the same thing as the number of vertices on the hull, right? But it turns out that this algorithm will eventually terminate when m is bigger than the number of the vertices on the hull, because at that point, this loop will have enough time to terminate and get finished, right? So the total cost of doing this thing is I have to basically do a sum from t equals 0 to the ceiling of the hyperlog, or it's like the log of the number of vertices on the hull, right, of this time complexity here, right, which is going to be n times log of 2 to the 2 to the t. And if you sum this all up, right, then what you'll get is basically this log will basically disappear. Then I'll have basically the sum of n to the 2 to the t, right? And if I sum this up, then I get basically a 0 to like log, whatever. And one of the logs cancels, right, because of the 2 there. And I just get basically an n log h, right? And that's the, or basically order of n log h. And I think that's it for today. We'll revisit orientation stuff. I'm already over time anyway. So we're done.